In East Chicago, Indiana, there lives a giant fiery beast. It's 30 stories tall, has a belly full of flames, and when lanced, bleeds molten metal. The Beast, a Goliath blast furnace affectionately known as Number 7, is the pride of the Middle Steel Company.
The blast furnace is the first step in the steel making process. Its role is to convert raw iron ore, which is a mixture of iron ore and oxygen and other impurities. The blast furnace melts the ore and it purifies the ore into a liquid metal that is 95% iron content.
Number 7 blast furnace, height 310 feet, consumes 20,000 tons of raw materials per day, produces 11,000 tons of liquid iron per day. Blast temperature 2,300 degrees Fahrenheit.
Built in 1980 by Inland Steel at a cost of $1 billion, Number 7 is the largest blast furnace in North America and the latest triumph in the quest to produce mass quantities of steel with the utmost efficiency. And to make steel, you need iron. Lots and lots of iron. The pursuit to harness and employ the versatile properties of iron dates back almost 5,000 years.
Mankind has been using iron since about 3000 BC. Archaeologists have found iron tools in the pyramids in Egypt. The first iron-making processes only produced a lump of hot iron that then had to be taken to a blacksmith forge and hammered into shape. They did not make liquid iron. A blast furnace produces liquid iron. The first blast furnace was developed in Belgium in the mid-1300s AD. These first blast furnaces were made of stone instead of steel. The wind was provided by a water wheel connected to a wooden and leather bellows, and the liquid iron was casted into molds, so it was a very simple affair and only made about 1 net ton per day.
The first stone furnaces used charcoal for fuel. In the early 1700s, coke, made from abundant coal, took its place, to the joy of trees everywhere. And about 30 years later, a hot blast made the slow process fast.
By putting hot compressed air in the furnace, it reduced the amount of fuel you needed in the furnace and increased the amount of iron ore you could charge. Therefore, the production rate could be increased. The larger volume of air that you inject into the blast furnace, the more coke you burn, the more ore you melt, the more iron that you make.
Bigger is better, which is why Number 7 is a state-of-the-art facility that has perfected the science of liquid iron production. The process begins as carefully controlled amounts of raw materials are carried up by conveyor and charged into the top of the blast furnace. The iron ore pellets and sinter, which removes impurities, are combined with coke, the fuel.
Just like baking a cake, we have to have so much of each ingredient to make the quality of iron that is desired by our customer.
We're on the furnace top, which is about 30 stories up from ground level. All material travels through this point. Behind me is the boiler house, which is used to supply the compressed hot wind to the furnace. It travels to the furnace via the pipe that you see below you.
At the same time we are charging raw materials in the top of the furnace, we are putting compressed air in the bottom of the furnace through a series of nozzles called tuyeres. The blast going in the bottom of the furnace causes the coke to burn. Just like when you take a bellows and fan the fire in your fireplace, this is the same effect that the compressed air has in the bottom of a blast furnace, and of course that's where the blast furnace gets its name.
We're standing on the Tuyer platform. It's where the hot gases are blown into the furnace. Right now we have a wind volume of about 230,000 cubic feet per minute being blown in at a temperature of 2,300 degrees Fahrenheit.
The compressed hot air meets the raw materials in the hearth, and a series of chemical and thermal reactions take place. The liquid iron descends to the bottom, And then, 12 times a day, the pneumatic steel drill, looking like a monster grasshopper, bores 11 feet into the blast furnace to extract the molten material. This is where the fireworks really begin.
Molten iron is coming out of the furnace. We call it hot metal. It's 95% iron, 4% carbon, 1% gangue material.
The spent tap hole is plugged, and the entire operation moves to the other side of the furnace. The hot metal is transported by refractory-lined rail cars, called PEW, or torpedo cars, to a basic oxygen furnace about a mile away. There, the purified liquid iron will be combined with scrap metal and alloys, subjected to a supersonic blast of pure oxygen, and further processed into industrial steel.
What makes number 7 blast furnace a world-class furnace is the size of this facility. It has a hearth diameter of 45 feet, which means we could put 2 blast furnaces of World War II vintage inside of number 7 blast furnace. It has 40 tweer openings in the bottom of the furnace, where most furnaces have half that amount. It has 4 tap holes. It is capable of making 11,000 tons a day. And it does this with the same number of people that was required to run one of the smaller blast furnaces over 50 years ago.
This big blast furnace incorporates the latest in technology. Unlike furnaces of decades past, most of this streamlined operation is controlled remotely.
This is number 7 blast furnace control room. We receive all communications in here. We weigh and batch materials on a remote basis and charge to the furnace. We monitor all of the process variables. We heat and fire the stoves. We also control the grinding and injection of the pulverized coal injection going into the furnace. The computer screen is a mimic of the material being discharged out of the stockhouse weigh bins, traveling up the primary conveyor belt. It's then charged to the furnace, and we do that cycling about 500 times per day.
This entire operation runs day in and day out, 365 days a year, with an annual liquid iron production rate of over 3.5 million tons. But number 7 is getting some competition.
In China and Korea, they are building new blast furnaces the size of number 7 because they are going through an industrial revolution and do not have enough steel to support the increase of infrastructure that is required to build bridges, highways, buildings, and their factories.
But because of the enormous productivity levels, the number of blast furnaces in the U.S. has decreased dramatically.
In 1946, there were 249 blast furnaces in operation, and in 2003, they are down to 33 blast furnaces. However, I suspect within the last 30 years, the total amount of iron produced in the United States has actually grown, even though the number of blast furnaces has gone down. This is because production is getting concentrated now in larger furnaces, which have higher production efficiency.
And the very largest and most productive of them all, number 7, lives here at this 19,000-acre steel-making facility, dedicated to the output of some seriously heavy metal.